The Voyager spacecraft did not make a sound when they passed through the heliopause. No alarms blared. No flash of light signaled the crossing. There was only the subtle shift in the behavior of charged particles and a faint tremble in the surrounding magnetic field. But what they entered was nothing less than myth made real: interstellar space. What lies beyond our solar system is not simply more space. It is a new kind of existence, colder, darker, and vastly more ancient than the worlds we've come to know. From the flaming cauldron of the sun to the edge of its faint breath, the solar wind, we had understood space as something filled with planets, with motion, with warmth, with gravity. But past the heliopause lies a realm where our star's influence ends, and something else begins. A realm of undiluted silence. Yet silence is not emptiness. This region, though nearly a vacuum, is alive with motion on scales we cannot easily sense. Here, the interstellar medium, an almost intangible blend of atoms, ions, cosmic dust, and magnetic fields, dances in slow, epochal waves. Each atom travels for years before encountering another. Each dust grain has seen more star births and deaths than any human mind could count. You might imagine this space as nothingness, but it is stitched together by forces and particles we barely understand. It is in this very nothingness that our journey truly begins. The Voyager probes, now elder emissaries of Earth, continue to drift outward, their golden records, etched with symbols and songs of humanity, carry our first attempt to introduce ourselves to the void. They are not just instruments. They are artifacts, prayers launched into the dark. They move at nearly 17 kilometers per second. But even at that speed, they crawl across the gulf to the next star. It will take 70,000 years before either could come remotely close to Proxima Centauri, our nearest stellar neighbor. And yet, they go. Beyond the heliopause lies a place of myth and probability, the Oort cloud. It is not a cloud in any visual sense, but a spherical shell of icy remnants, a ghostly halo of comets and proto-worlds, perhaps trillions of them, orbiting our sun from such vast distances that one full revolution might take 1,000,000 years. We've never seen it directly. We infer its guidance from the long arcs of comets that fall toward the sun from the deep night. These are whispers from the edge, bearing witness to the solar system's primordial formation, and carrying the fingerprints of times before Earth even had oceans. If we could stand at the outer rim of the Oort cloud, the sun would be nothing more than a bright star, indistinguishable from its cousins. Here, the solar system ends, not with a wall, but with a gradient, a slow fading of influence into the galactic tide. This is where the solar system blurs into the interstellar medium, a zone that defies human intuition. It is not a place, but a process, a continual exchange between what belongs to a star and what belongs to the galaxy. The interstellar medium is not still. It is shaped by colossal events. Supernovae puncture its serenity with shock waves. Stellar winds from young suns carve out caverns and cavities. These collisions form super bubbles vast, irregular voids, where cosmic matter thins like mist in a canyon. And through these bubbles, high-energy cosmic rays scream across the dark, born in distant cataclysms and accelerated by magnetic chaos. Each one is a particle with a story, a messenger from across time and space. Sometimes this interstellar material finds us. The object called Oumuamua entered our solar system like a letter with no return address. It did not behave like any comet or asteroid we had seen. It accelerated slightly as it left the sun, spun like a tumbling shard, and glinted with puzzling reflectivity. Its shape, long and narrow, was more science fiction than astronomy. Was it a fragment of a shattered world? A derelict probe from another civilization? A shard of interstellar ice? We still do not know, and that uncertainty is part of its power. A few years later came Borisov, the first unequivocal interstellar comet. Unlike Oumuamua, Borisov behaved more familiarly, releasing gas and forming a tail. But its composition was subtly different, suggesting that even the most mundane comet from another star holds secrets unfamiliar to Earth. These wanderers are more than curiosities. They are cosmic introductions, the universe saying, "You are not alone in this complexity." As we drift outward in thought, we reach the Alpha Centauri system, 3 stars, one of which hosts a planet in its habitable zone. Proxima Centauri b, slightly larger than Earth, may hold liquid water. It is bathed not in our sun's light, but in the cool, red glow of a diminutive star. Days there may be eternally twilight. If there is life, it has evolved beneath a sky where the sun never sets. Most nearby stars are red dwarfs, quiet, dim, long-lived. They do not blaze like our sun. They simmer. They might offer the best chance for long-term habitability, but their flares, when they occur, are ferocious, potentially stripping planets of atmospheres. A delicate balance exists, one we have only begun to study. Within 20 light-years of Earth, over 60 stellar systems orbit in a slow, cosmic waltz. Each carries its own family of planets, perhaps their own oceans and deserts, clouds and storms, questions and silences. Some planets may be locked in eternal day or night. Others may orbit 2 suns, casting dual shadows. Still others may lie beneath thick blankets of hydrogen or ice, shielding biospheres unlike anything we know. The sun, once our sole concern, is now a local participant in a much broader network. We are one note in a galactic symphony. And this music, this immense gravitational choreography, continues across tens of thousands of light years, leading us inexorably to the Milky Way's grand spiral. The broader context of all we are, we. But before we go there, we pause, because even here, in interstellar space, in this realm of shadows and whispers, we are surrounded by a kind of memory. A memory written not in books or songs, but in the orbits of comets, the tremble of magnetic fields, and the silent drift of probes that left our world before most of us were born. This is where the solar system ends and where the galaxy begins. Somewhere between the comets of the Oort cloud and the faint tug of Proxima Centauri, we find ourselves no longer thinking about stars as destinations, but as inhabitants of something larger, a structure vast enough to contain billions of suns, yet intricate enough to give birth to complexity. We live inside a spiral. Not just a spiral of stars, but a spiral of time, gravity, and memory. The Milky Way. Our galaxy is a wheel of fire 100,000 light years across, slowly turning through the dark. It is not a solid disk. It is a living system, evolving, churning, continuously reshaping itself under the influence of unseen forces. At the core of this structure lies Sagittarius A, a supermassive black hole with a mass of 4 million suns. It does not devour the galaxy, as myths might suggest. Instead, it anchors it. Like a stone in a whirlpool, stars orbit it in dizzying speeds, whipped by its gravitational pull, creating one of the most energetic regions in the known universe. Near this core, time slows, space warps, and light bends. Yet from our quiet place in the Orion Arm, some 26,000 light years away, we see only the faint, milky glow of its distant signal. Our sun takes 225 million years to complete one orbit of the galactic center. Since its birth, it has circled the galaxy about 20 times. Each of these galactic years is long enough for mountains to rise and fall, species to appear and vanish, oceans to form and dry. Humanity has existed for only a fraction of one such orbit, a blink in cosmic time. But even this orbit is not smooth. It is shaped by the gravitational pull of neighboring stars, molecular clouds, and most mysteriously by dark matter. This invisible substance surrounds our galaxy in a vast halo, extending well beyond the edge of the visible disk. We cannot see it, but we can feel its pull. Without dark matter, the stars on the edge of the galaxy would fly apart. Its presence is the scaffolding on which the Milky Way is built. Embedded in the spiral arms are stellar nurseries, colossal clouds of hydrogen and dust, where gravity begins its quiet work. These clouds collapse under their own weight, fragment, and ignite. The result is stars burning spheres of nuclear fusion, each born from chaos, each destined for a unique journey. And not all stars are born equal. Some are massive, living short, brilliant lives before dying in supernovae explosions, so powerful they outshine entire galaxies for a moment. Others are small, steady, and long-lived, like red dwarfs, simmering for trillions of years. Each star carries the chemical memory of the cloud that birthed it. And from that memory come the ingredients of life. In the spaces between the arms, stars drift like forgotten thoughts. These are the older populations, red giants, white dwarfs, the remains of generations that lived and died before Earth was formed. Some travel alone, others belong to ancient clusters, bound together for billions of years by mutual gravity. To stand beneath a dark sky and see the faint band of the Milky Way is to peer sideways through this galactic disk. What appears as a smear of starlight is, in fact, a corridor of depth, layer upon layer of history, extending thousands of light years in all directions. But we do not live in isolation. The Milky Way is not a solitary wanderer. It is one of many in a local cluster of galaxies, the local group held together not by proximity alone, but by gravity's slow insistence. The Andromeda Galaxy, our sister spiral, is the most massive member of this group. It lies 2.5 million light-years away, and it is moving toward us at a speed of 110 kilometers per second. In 4 billion years, the two galaxies will merge, and yet this collision will not be violent in the way we think. Stars are so far apart that very few will actually collide. Instead, their gravitational fields will twist and warp. Stars will be flung into new orbits, and the gas and dust within both galaxies will spark new waves of star formation. Over time, the chaos will settle into a new equilibrium. What remains will not be a spiral, but a vast elliptical galaxy, a silent monument to cosmic change. Already, the Milky Way is not pristine. It bears the scars of previous mergers. Streams of stars, remnants of smaller galaxies thread through the halo, invisible to the naked eye, but traceable by telescopes and simulation. These star streams are the fossil record of galactic evolution, showing us that our home is not static, but rather an ongoing act of assembly. And around the Milky Way, like satellites circling a planet, orbit dozens of smaller galaxies. The Magellanic Clouds, visible from the southern hemisphere, are among the brightest. These dwarf galaxies are not just companions, they are donors. They shed gas and stars into the Milky Way, slowly becoming part of it. The boundary between one galaxy and another is not a wall. It is a flow, a negotiation of gravity and time. The farther we look, the more interconnected everything becomes. Between the stars, the interstellar medium continues its silent work. Dust grains, formed in the atmospheres of dying stars, seed the birth of new planets. Magnetic fields twist through the gas, shaping its motion. Supernovae shockwaves compress clouds and initiate new cycles of formation. The galaxy breathes not in hours or days, but in epochs. And we tiny creatures on a pale blue dot are part of this breath. Every atom in your body was once inside a star. The iron in your blood, the calcium in your bones, the oxygen you breathe, all forged in stellar cores and scattered across the galaxy in death. You are a galactic heir, a child of thermonuclear fire and cosmic dust, a thinking structure of star stuff, capable of turning inward and asking why. In mapping our galaxy, in measuring its arms and tracing its center, we are not just cataloging stars. We are recovering our origin story, not just of where we live, but of how life itself came to be. The Milky Way is not our backdrop. It is our birthplace. Mom. And yet, it is only the beginning. As we continue outward, we encounter the local group as a whole. 50 galaxies, vast in diversity, bound together in a slow dance that will take billions of years to play out. This is not just a galactic family. It is a prelude to something larger, a thread in the cosmic web whose vastness dwarfs even our spiral's grandeur. The night sky, viewed from Earth, seems calm. Stars twinkle with quiet dignity, and the Milky Way draws a faint, glowing band across the darkness. But if you could step back far, far back, you would see something profoundly different. A tangled web of matter, stretched across the cosmos, like a neural network of a sleeping giant. This is the universe, as it truly is, not random, not empty, but organized by the silent hand of gravity. We call it the cosmic web. At the heart of this structure are superclusters, immense groupings of galaxies, strung together into filaments that span hundreds of millions of light years. The Milky Way, along with the Andromeda Galaxy and their companions, resides in a cluster of galaxies known as the local group. But even that is just one node in a larger filament, the Virgo supercluster, which itself is part of something even grander, a gravitational basin we call Laniakea. Laniakea, meaning immeasurable heaven in Hawaiian, is not a formal boundary, but a flow. It encompasses over 100,000 galaxies, spanning 500 million light years, all moving along cosmic rivers toward a common attractor, a region of deep gravitational pull, unseen but felt across the sky. We do not orbit this center. We are being drawn toward it, along with thousands of other galaxies, like leaves drifting in a current whose source remains mysterious. Galaxies, in these superstructures, are not stationary islands. They move swirling, falling, threading, all within invisible scaffolding woven by dark matter, the unseen architecture that holds the visible universe in place. Though we cannot observe dark matter directly, its gravitational imprint is undeniable. Without it, these colossal structures would not exist. The luminous matter, stars, gas, and dust is merely the glowing tip of an enormous invisible iceberg. If you imagine the universe as a sponge, the galaxies are concentrated along the thin filaments, the threads, while the vast voids in between are mostly empty. These voids, often hundreds of millions of light years across, are some of the largest and loneliest regions known. They are not truly empty, but the density of matter is so low that a galaxy might wander for eons without encountering another. These voids form the spaces between the strands of the web, just as rivers form the boundaries between continents. And yet, even in these barren expanses, physics remains elegant. In the emptiest places, the expansion of the universe is most pristine, unimpeded by the gravity of nearby galaxies. There, the Hubble flow, the cosmic stretching of space, continues unchallenged, offering a glimpse into the raw expansion that defines our cosmos. The great filaments are the arteries of cosmic structure. They carry gas, dust, and galaxies, the raw material of creation, toward the dense nodes where galaxy clusters form. These clusters are enormous, containing thousands of galaxies, vast reservoirs of hot gas, and central elliptical behemoths, often the cannibalistic remains of smaller galaxies merged together. Among the largest of these is the Virgo cluster, located 65 million light-years away. It contains over 1,500 galaxies, and its gravity governs the motion of many surrounding systems, including our own local group. It acts as a regional capital in the cosmic hierarchy, not by power, but by mass and pull. The Virgo cluster is the dominant feature of the local universe, and it draws us toward it silently, constantly. But even the Virgo cluster is just one part of the Laniakea supercluster. And Laniakea is itself woven into something still more immense, a network of superclusters that stretches to the edges of the observable universe. These threads are not evenly spaced. Some are thin, others thick, some bend, others cross. And in the regions where multiple filaments meet, gravity compacts the material into walls, immense planar structures that rival anything we've seen. The largest known of these is the Hercules Corona Borealis Great Wall, a structure spanning over 10 billion light-years. If you could see it, it would appear as a vast wave of galaxies, frozen in place by cosmic expansion. Its sheer scale challenges our understanding of the universe's early growth. The existence of such massive formations has led some cosmologists to wonder whether our theories of inflation and dark energy require revision. To map these structures, astronomers conduct redshift surveys measuring how the light from distant galaxies is stretched by cosmic expansion. The Sloan Digital Sky Survey and its successors have mapped the positions of millions of galaxies, creating a 3D model of the universe that is both beautiful and humbling. In these maps, galaxies appear not as points, but as brushstrokes in a larger composition. The universe is not chaotic. It is patterned. And this pattern did not emerge randomly. It was seeded in the earliest moments after the Big Bang in quantum fluctuations. Tiny irregularities in the density of energy that were inflated to cosmic scales during the first fraction of a second. These irregularities acted as gravitational wells. Over billions of years, matter fell into them, forming stars, galaxies, clusters, and finally, the web we see today. This process, the transition from quantum jitter to galactic symmetry, is one of the most awe-inspiring transformations in all of science. It is as if the universe translated uncertainty into form, probability into architecture. The cosmic web, in many ways, mirrors our own neural networks. Both are systems of nodes and connections, shaped by interaction, memory, and flow. Some have even speculated, half seriously, half in metaphor, that the universe resembles a kind of consciousness, or at least that its large-scale structure shares traits with cognition. While this remains philosophical, It points to a deeper truth that pattern and connection emerge naturally in systems governed by feedback and growth. What, then, does it mean to live inside such a structure? It means that we are not adrift in an indifferent expanse. We are bound not just by gravity, but by context. Every atom in your body, every cell, every breath owes its structure to the shape of this web. Your existence is not an accident. It is a product of cosmic organization, born in a place where matter gathered, where stars ignited, and where chemistry was allowed to become biology. As we move farther from Earth, farther from our own galaxy, we do not leave behind the story of life. We expand it. The stars are not decorations. They are witnesses. And the cosmic web is not just a structure of matter, but of meaning, an archive of the universe's own self-organization. Eventually, we will reach the edge, not of the universe itself, but of what we can observe, a horizon beyond which light has not yet had time to arrive. But before that, we must pass through the veil of the cosmic microwave background, the fossil light of creation. There, at the edge of visibility, lies a record of everything that came before, and perhaps hints of what lies beyond. From the great walls of galaxies to the luminous filaments stretched across billions of light years, we ascend one final step toward the ultimate limit, the edge of observation itself. Here, the light we receive is not from stars or galaxies, but from the very fabric of the early universe. It is the faint, uniform glow of the cosmic microwave background, a ghostly whisper from 13.8 billion years ago, when the universe first became transparent. At that moment, roughly 380,000 years after the Big Bang, the hot plasma that had filled space cooled just enough for protons and electrons to combine into neutral atoms. Photons, previously trapped in a dense fog of charged particles, were finally free to travel. That light has been moving ever since, stretched by the expansion of space into the cold microwave radiation we detect today. It arrives to us from every direction, carrying within it the imprint of primordial structure. Tiny temperature fluctuations in this ancient light, just a few millionths of a degree, tell us volumes. They map the seeds of galaxies and superclusters. They reveal the initial conditions of our cosmos, and they speak of a profound, nearly perfect symmetry, broken just enough to give rise to all we see. Yet, even these ancient photons do not reach infinitely back. Before that light, there was darkness, not metaphorical, but literal, a period we call the Cosmic Dark Ages. For hundreds of millions of years after the Big Bang, there were no stars, no galaxies, no light at all, only a cooling, expanding ocean of hydrogen and helium. This was a time of silence in the cosmic story, a prelude to the first flare of starlight. Then came the cosmic dawn. As gravity drew the primordial gases together, the first stars ignited. Their radiation began to ionize the hydrogen fog, carving luminous bubbles into the darkness. Galaxies began to form. Black holes awakened. And the structure of the modern universe was set in motion. These first lights are among the faintest, most distant objects we can observe, and yet they mark the turning point from potential to form. But beyond even this ancient frontier lies a deeper mystery. What happened before? To understand this, cosmologists turn to a revolutionary theory, cosmic inflation. According to this idea, the universe underwent an exponential expansion during the first tiny fraction of a second after its birth. During this inflationary epoch, space itself expanded faster than the speed of light, not in violation of relativity, but because relativity places no limit on the expansion of space itself. Inflation stretched quantum fluctuations, microscopic jitters in the vacuum to macroscopic scales, planting the seeds of galaxies and voids. It smoothed the universe, explaining its large-scale uniformity, and it carried regions that were once in contact beyond each other's horizons, solving the so-called horizon problem, the question of how distant regions of space look so similar despite having never exchanged information. Inflation is more than a mathematical fix. It is a window into the earliest possible time, a moment when the universe, governed by strange fields and perhaps higher dimensions, unfolded its very architecture. But inflation, as profound as it is, raises a new possibility. What if it never truly ended? In the theory of eternal inflation, some regions of the universe stop inflating and form bubble universes like ours, while other regions continue to expand. This process, eternal into the future and potentially the past, creates a fractal landscape of countless universes, the multiverse. In this model, our observable universe is just one bubble in a much larger, perhaps infinite, ocean. Other bubbles may have different physical constants, different numbers of dimensions, even entirely different laws of physics. Some might harbor life, others may be sterile or collapse moments after birth. We exist in a region where the conditions permit complexity, not by cosmic design, but by statistical inevitability. This idea, while difficult to test directly, has explanatory power. It offers a natural solution to the fine-tuning problem, the observation that the constants of physics seem perfectly balanced. To allow life in a multiverse, it is not surprising to find ourselves in a universe where life is possible. It would be more surprising to find ourselves anywhere else. Yet, not all multiverse models arise from inflation. Quantum mechanics, too, suggests plurality. In the many worlds interpretation, every quantum event branches into multiple outcomes, each realized in its own parallel world. Every decision, every fluctuation, every subatomic collision creates new paths, infinitely diverging timelines, some eerily close to ours, others wildly alien. And string theory, our most ambitious attempt at unifying physics, predicts a landscape of possible universes, each with its own configuration of extra dimensions and vacuum states. These models envision a meta-space, or bulk, where brains, multidimensional universes float like sheets in a cosmic wind. occasionally colliding or interacting. Could these other universes ever touch ours? Some theorists speculate that if our bubble universe once collided with another, it might have left a scar in the cosmic microwave background, a circular anomaly. A cooler or hotter spot where the collision disturbed the infant cosmos. Searches for such imprints continue, but so far, no definitive signal has been found. Yet, even in the absence of evidence is revealing. It sharpens our theories. It draws boundaries around what we can know and reminds us of what we cannot. Still, the idea that the universe might be infinite in extent and not just in space, but in possibility, evokes an ancient longing. To ask what lies beyond the stars is also to ask what lies within us. For we are made of the same stuff, born of the same burst of energy, governed by the same laws, and shaped by the same expansion that carried galaxies apart. When we contemplate the multiverse, we do not escape the laws of physics. We expand them. We test their scope. We ask whether the patterns we observe atoms, molecules, stars, minds are unique or commonplace, universal or contingent. And in that asking, we find something deeply human, the refusal to accept a final horizon, the urge to step beyond the visible, the known, the safe. Beyond the galaxies, beyond the filaments of dark matter, beyond even the most speculative realms of the multiverse, the universe begins to curve inward, not in space, but in understanding. Here, we no longer ask where or what, but why and how long. The most enigmatic entities that nature has revealed are not stars or planets, but voids within them, black holes. When a massive star ends its life, its own weight crushes it inward. No pressure resists. The collapse continues until all matter is compressed to an infinitely dense point, a singularity hidden behind an invisible veil known as the event horizon. Inside this horizon, not even light escapes. Causality unravels. Space and time trade roles. The future, for anything that falls in, ends at the singularity. And yet, this region may not be an end at all, but a tunnel. Wormholes, mathematical bridges through space-time, emerge as theoretical solutions to Einstein's equations. They suggest that black holes might connect to other regions of the universe, or to other universes altogether. Could a black hole be a cosmic seed, the beginning of something new? Some speculative models propose that each black hole might birth a new universe, pinched off from its parent. The singularity becomes a bounce. The horizon becomes a womb. If true, our universe might itself be the interior of a black hole formed in another cosmos. Yet, despite their mysteries, black holes are not eternal. In 1974, Stephen Hawking showed that black holes radiate. Through quantum processes near the event horizon, pairs of virtual particles are separated. One falls in, the other escapes. This Hawking radiation slowly drains the black hole's mass. Over incomprehensible timescales, trillions of years, even the largest black holes will evaporate, leaving behind only fading heat. But this leads to a paradox. What happens to the information about the matter that fell in quantum mechanics insists that information is never destroyed? Yet, if the radiation is featureless and the black hole vanishes, the story seems lost. One proposed resolution is the holographic principle. The idea that all the information inside a region is encoded on its boundary, like a three-dimensional object projected onto a two-dimensional surface. Reality may be a hologram. Our universe could be such a projection, its deep laws playing out not within, but at its edges. If true, this insight redefines the very nature of space and time. It bridges gravity and quantum mechanics, the two great frameworks of physics that, until now, have resisted unification. Their conflict becomes most intense in the Planck regime distances on the order of 10^35 meters, energies near 10^19 GeV, where quantum effects of space-time itself must be reckoned with. Here, smooth geometry shatters, space-time foams. Singularities may dissolve into loops or vibrating strings. String theory. One proposed unifier replaces point particles with one-dimensional strings. Their different vibrational modes give rise to the zoo of particles we observe. But for string theory to work, it requires extra dimensions, 6 or 7, beyond the familiar 3 tightly curled or hidden. These dimensions might harbor other universes, separated from us, not by distance, but by orientation in higher dimensional space. Other approaches, like loop quantum gravity, suggest that space and time themselves are quantized, composed of discrete units, like the pixels of a screen. If space-time is granular, it might avoid the infinities of classical theories. Singularities might be smoothed. Time itself might become emergent, not a fundamental flow, but a relational quality that arises from deeper order. As we look ahead, one question looms. What will become of time? 3 major fates confront the universe. In the Big Crunch, gravity wins. If the universe contains enough matter, expansion halts and reverses. Galaxies collapse inward. Temperatures rise. Time ends where it began in fire. In the Big Freeze, dark energy prevails. The universe expands forever. Stars die. New stars cease to form. Black holes evaporate. Eventually, only radiation remains, scattered across an ever-thinning vacuum. The cosmos becomes a cold, dark whisper of its former self. No structure, no memory, just entropy. In the Big Rip, the most dramatic scenario, dark energy grows stronger. Eventually, it overcomes all forces, ripping apart galaxies, stars, planets, even atoms. Space itself tears. Time ceases, not in heat or cold, but in disintegration. And yet, there are more speculative ends. In the Big Bounce, collapse is halted by quantum effects. A new expansion begins. The universe cycles eternally, each cosmos born from the ashes of the last. Others imagine false vacuum decay, where a sudden shift in the vacuum energy creates a new reality, rewriting the laws of physics at light speed, erasing everything before it. But endings are also beginnings. To ask about the fate of the universe is to confront the boundary of our theories and the limits of our perception. It forces us to ask what time is, what being means, and whether the universe is a story with a final page or a poem that loops. Perhaps the most haunting possibility is that we will never know, that the universe's fate will unfold on timescales so vast that no consciousness can witness them, that the last thought, the last photon, the last motion will pass unnoticed. And yet, the fact that we can ask, that we can map billions of light years, hear the echo of the Big Bang, simulate quantum foam and multiverses, is itself a miracle. The mind, born of dust, reflects on the stars and writes their history in language and light. So when you look up tonight, let the stars remind you, you are not at the center of the universe, but you are central to the universe becoming known. That is what lies beyond, not a place, not even a theory, but the widening horizon of understanding.
Light from a star 4 light-years away reaches your eyes tonight, carrying a glimpse of its past, a moment when Earth's oceans were younger and humanity's gaze was fixed on simpler skies. That star, perhaps Proxima Centauri, faint and red, whispers of distances vast yet measurable, a mere step in the cosmic tapestry. From Earth's surface, the naked eye catches about 2,000 stars, each a pinprick of light that has traveled years, centuries, or millennia to meet you. With binoculars, this number swells to 12,000, revealing fainter beacons that hint at the galaxy's deeper layers. Our Milky Way alone harbors 100 billion stars, and the observable universe stretches further, holding 10 to the power of 20 stars, a number so immense it dwarfs the grains of sand on every shore. This vastness begins with a single photon's journey, governed by the speed of light, 300,000 kilometers per second. When you look at Sirius, the brightest star in the night sky, you see it as it was 8 years ago, its white dwarf companion too faint to discern without a telescope. Astronomers, since Hipparchus in the 2nd century BC, have measured such brightness using magnitudes. A first magnitude star, like Sirius, shines with a brilliance 100 times greater than a 6th magnitude star, barely visible to the unaided eye. George Pogson, in 1850, refined this scale. Each magnitude step corresponds to a brightness decrease by a factor of 2.5. A second magnitude star is 2.5 times fainter than a first, and a star of magnitude 5 is 100 times dimmer than the brightest. These measurements rely on units like magnitudes and parsecs, terms astronomers cling to despite physicists' preference for meters and kilograms. A parsec, roughly 3.3 light-years, feels intuitive when charting distances to stars like Alpha Centauri, a triple system where 2 stars dance too closely to be distinguished without aid, while Proxima lingers slightly nearer. Such units, though arcane, anchor our understanding of a universe where centimeters or grams suffice. As the scales of stars and galaxies render the difference trivial, imagine measuring the distance to a galaxy in meters. It's like counting the steps to a distant city when a map's scale offers clarity. Stars themselves are more than light sources. They are cauldrons of transformation. Most matter in the universe exists as plasma, a state where atoms, stripped of electrons, roam freely at temperatures exceeding thousands of Kelvin. In a star's core, plasma churns, fusing hydrogen into helium, releasing energy that lights the cosmos. On Earth, solids hold atoms in rigid lattices, liquids allow them to slide, and gases let them drift. But in stars, plasma dominates, a fluid of ionized particles that powers their glow. Picture a campfire, its flames, though gaseous, pale beside the sun's plasma, where temperatures reach millions of Kelvin, driving fusion that Earth's scientists dream of replicating. Fusion, the sun's heartbeat, eludes our grasp. Deuterium, heavy hydrogen abundant in oceans, could fuel reactors if we could overcome the electrical repulsion between nuclei. In stars, gravity and heat force nuclei together, but on Earth, we heat deuterium gas to tens of millions of Kelvin. Seeking controlled fusion, the hydrogen bomb, triggered by fission, achieves this violently. But a star composed solely of deuterium would erupt catastrophically. Our challenge lies in containing such heat long enough for nuclei to merge, a puzzle unsolved despite decades of effort. Imagine a furnace so hot it melts its walls. Our fusion reactors face this barrier, yearning to mimic the star's quiet alchemy. This quest echoes humanity's curiosity about stellar origins. In 1862, William Thomson proposed the sun's heat came from gravitational contraction, calculating its age at 20 million years, a span too brief for Earth's geological record. Radioactivity's discovery revealed a solar system billions of years old, ending the debate. The Helmholtz-Kelvin timescale, though outdated, remains useful, describing how radiant energy diffuses from a star's core. Today, we know the sun burns hydrogen, not contracts, sustaining life for 4.6 billion years. Each star's light, then, is a story of endurance, a signal crossing space to meet our gaze, inviting us to ponder what lies beyond the visible. A photon from a galaxy 13 billion light-years distant brushes past a telescope on a mountain peak, its journey beginning when the universe was a toddler, barely a billion years old. That light, stretched by the universe's growth, arrives redder than when it left, a testament to the cosmos swelling like a river, widening as it flows. The universe, born 13.8 billion years ago in the Big Bang, is not a static stage but a dynamic expanse, carrying galaxies apart as space itself stretches. Edwin Hubble, in 1929, noticed this motion galaxies recede, their light shifting toward the red end of the spectrum, a cosmic Doppler effect akin to a siren fading as it speeds away. The farther a galaxy, the faster it retreats, a pattern now called Hubble's law. This expansion sets the boundary of what we can see, a sphere roughly 46 billion light-years in radius. Despite the universe's youth, why so vast? Space has grown since the light we now see was emitted, like a message sent from a ship that since sailed far beyond its starting point. The observable universe isn't hemmed by walls, but by light's finite speed, 300,000 kilometers per second. Beyond this horizon lie galaxies whose light hasn't yet reached us, and some, due to the universe's accelerating growth, never will. Imagine a letter sent from a distant shore, carried by a current faster than any ship can row. It's lost to us forever. In 1998, astronomers discovered this acceleration, a surprise that upended expectations. Gravity, which pulls matter together, should slow the universe's expansion, like a stone arcing back to Earth. Instead, galaxies race apart faster each moment, driven by dark energy, a force acting like an invisible wind pushing against gravity's embrace. This energy, making up 68% of the cosmos, remains a mystery. Picture a fabric stretched taut, then pulled ever wider by an unseen hand. That's our universe, reshaped by a force we can't yet grasp. Some propose dark energy is a property of space itself, a constant energy woven into the vacuum, as Einstein once speculated with his cosmological constant in 1916. Others imagine dark energy as a dynamic field, dubbed quintessence, shifting over time, perhaps altering the universe's fate. If stronger, it could tear galaxies, stars, even atoms apart in a big rip. If weaker, the universe might collapse in a big crunch. For now, it promises a big chill, where galaxies drift so far apart that stars burn out, leaving a cold, sparse void. This expansion redraws our cosmic map daily, pushing more galaxies beyond our horizon. A galaxy 10 billion light-years away today sends light that will arrive in far more than 10 billion years. As space between us grows, some galaxies, too distant, are already beyond reach. their light forever outpaced by expanding space. This boundary, the cosmic event horizon, isn't a physical edge but a limit of perception, like the curve of a hill hiding a valley beyond. In ancient times, thinkers like Archytas in the 5th century BC pondered cosmic edges. He asked if a spear were hurled past the universe's boundary, would it rebound or vanish? The question exposed the paradox of a bounded cosmos. Something must lie beyond any limit. Epicurus, in the 4th century BC, argued the universe has no edge, infinite and filled with stars. Lucretius, a century later, echoed this, imagining a dart thrown at the cosmos's end, always finding more space. These ideas resonate today. Our universe may be infinite, or finite yet edgeless, like a sphere's surface where no boundary exists. Consider a balloon surface, dotted with galaxies. As it inflates, every dot moves apart, with no center or edge. Our universe behaves similarly, with no cosmic center Earth. The Sun or the Milky Way holds no special place. This is the location principle, asserting no point is privileged. The containment principle complements it, stating the universe holds all physical things, including space and time. Space isn't a void where the universe sits, it's part of the cosmos, expanding with it. The Big Bang wasn't an explosion into pre-existing space, but the birth of space itself, everywhere at once. If infinite, the universe was infinite at its start. If finite, it remained so, with no edge to cross. This challenges intuition. Picture standing on a shore, watching waves carry ships beyond sight. In the cosmos, there's no shore, no cliff where space ends. A traveler moving straight ahead in a finite universe might return to their start. Like circling a globe, astronomers search for such loops in the cosmic microwave background, a snapshot of the universe at 380,000 years old, when it cooled enough for light to travel freely. Its uniformity suggests the universe's vastness, but faint patterns could hint at a finite, looped topology, like a cosmic quilt stitched at its seams. These boundaries shape our cosmic story. Galaxies beyond the horizon exist, perhaps with stars and planets, but their light is a message we'll never read. As dark energy drives expansion, more galaxies slip beyond our grasp, like friends fading into a crowd. In trillions of years, only our local group Milky Way and its neighbors will remain visible, a lonely island in a darkening sea. Future observers might see a universe far smaller than ours, unaware of the vastness we glimpse today, their cosmic history dimmed by the relentless stretch of space. A single atom in your hand, vibrating with the energy of its electrons, owes its stability to a delicate balance of forces, tuned by constants like the speed of light, 300,000 kilometers per second, and the gravitational constant, a whisper of attraction between masses. These numbers, etched into the fabric of our universe, seem perfectly set to allow atoms to form, stars to ignite, and life to emerge. Change the electric charge of a proton by a fraction, and nuclei might collapse or never bind. Tweak gravity's strength, and stars could burn out too swiftly for planets to cradle life. This fine-tuning raises a question: why is our universe so hospitable to complexity, to creatures who gaze at its stars? Imagine a cosmic loom, weaving countless realities, each thread a universe with its own set of constants. In some, gravity is so fierce that matter collapses instantly. In others, it's too weak, and stars never form. This is the multiverse, an ensemble of universes, each a separate tapestry with its own rules. Our universe, with its 100 billion galaxies and 10 to the power of 20 stars, might be just one weave among infinite others. The idea stems from cosmic inflation, a theory suggesting that fractions of a second after the Big Bang, 13.8 billion years ago, space expanded exponentially, ballooning from smaller than an atom to vast beyond measure. In this model, inflation didn't end everywhere at once. Picture a pot of water simmering, bubbles forming and bursting unevenly. Some regions of inflating space cooled into universes like ours, with stable atoms and long-lived stars. Others kept expanding, spawning new bubbles, each with different constants. In one, the speed of light might be sluggish, dimming stars to mere glows. In another, Planck's constant could amplify quantum effects, making matter shimmer unpredictably. These bubble universes, isolated by expanding space, form a multiverse, each realm beyond our reach, like islands separated by an unbridgeable sea. Another multiverse arises from quantum mechanics, where reality splits at every choice. When an electron's spin is measured, two universes might emerge, one where it spins up, another where it spins down. Imagine tossing a coin and spawning realities for heads and tails, each branching infinitely. In some, you're stargazing tonight. In others, the sky is clouded. These parallel worlds, layered like pages in a book, share our constants but diverge in events. A cosmic library of every possible story. A third multiverse, born of string theory, posits our universe as a three-dimensional membrane floating in higher dimensional space. Other membranes, mere whispers away, might host universes with extra dimensions, where time flows backward or gravity repels. This multiverse offers a lens for the anthropic principle, which notes our universe's constants suit life because we're here to observe them. Robert Dickey, in 1961, framed this weekly. Our observations are biased by our existence. Brandon Carter, in 1974, proposed a stronger version. The universe must allow life at some point. Picture a cosmic lottery with countless tickets, each a universe. Only one ticket, ours, has the numbers for life, so we hold it. In most universes, atoms might not form, leaving only hydrogen gas, or stars might flare too briefly for evolution. Life, as we know it, needs carbon, oxygen, and stable planets warmed by stars like our sun, conditions rare in the multiverse's vast draw. Consider a universe where gravity is twice as strong. Stars burn faster, dying in millions, not billions of years, too swift for life to take root. Or one where the electromagnetic force is weaker, so atoms barely hold together, like sandcastles crumbling in a breeze. These scenarios suggest our universe's constants are either fortuitous or intentional. The anthropic principle leans toward chance among infinite universes. One was bound to fit us. Alternatively, a purposeful design could explain this tuning, as deists like Thomas Burnet argued in 1687, likening the cosmos to a clock wound once to run perfectly. Yet, science seeks explanations beyond intent, probing whether constants might derive from deeper laws. What if time itself varies across the multiverse? In our universe, time flows forward, marked by entropy's rise, like a river carving a canyon. In another, time might loop, events repeating endlessly, or splinter into multiple streams, each moment spawning new realities. Such universes challenge our sense of causality, where cause precedes effect. Life there might perceive existence as a mosaic, not a line, adapting to realities we can't fathom. These speculations stretch the boundaries of physics, suggesting our universe is one note in a cosmic symphony, each universe playing its own melody. The multiverse, though unobservable, isn't mere fantasy. Patterns in the cosmic microwave background, the universe's oldest light from 380,000 years after the Big Bang, could hint at collisions with other bubble universes, like ripples from stones tossed into a pond. No such evidence exists yet, but future telescopes might detect subtle anomalies. Quantum entanglement, where particles share states across vast distances, could also link our universe to others. Imagine two particles, entangled at the Big Bang, one now beyond our horizon. Measuring one might reveal secrets of realms we'll never see, a faint thread connecting isolated realities. These ideas redefine boundaries, not as edges but as limits of possibility. Our universe, with its fine-tuned constants, feels like a tailored suit, fitting life perfectly. Yet, in the multiverse, countless ill-fitting suits exist, lifeless and chaotic. The anthropic principle reminds us we're here because this universe allows it, but it doesn't explain why such a universe exists. Perhaps a future theory will tie constants together, showing they could only be as they are, like a puzzle with one solution. Until then, the multiverse stretches our imagination, a realm where every possibility plays out, unseen, beyond the horizon of our cosmic home. A neuron fires in your brain, sparking a thought about the stars overhead, each a distant furnace burning for billions of years. That thought, fleeting and intangible, arises from physical processes, atoms, electrons, and chemical bonds, yet feels distinct, as if it transcends the matter that birthed it. This tension between mind and matter mirrors a deeper question: what defines the universe's reality? The containment principle asserts that everything physical, stars, galaxies, even the space between them, exists within the universe, and nothing physical lies beyond. Space and time, not mere voids, are active players, bending under gravity's pull, stretching with cosmic expansion, as real as the ground beneath your feet. Picture a tapestry woven from space-time. Its threads the orbits of planets, the arcs of light from distant quasars. This tapestry holds all that is physical, from the plasma in a star's core to the faint cosmic microwave background, glowing since the universe was 380,000 years old. Archytas, in the 5th century BC, challenged the idea of a cosmic edge, asking what happens to a spear hurled beyond the universe's limit. Lucretius, centuries later, argued no such limit exists, as any boundary implies something beyond. Modern cosmology agrees the universe, whether infinite or finite, has no edge. A finite cosmos might curve back on itself, like a globe where every path returns home, but no wall marks its end. This principle excludes the non-physical. Imagine a realm of pure thought, untouched by matter or time. Such a place, if it exists, lies outside the universe's physical bounds, inaccessible to telescopes or equations. Yet, your thoughts, emotions, and consciousness emerge from physical processes, neurons firing, synapses crackling. Are they merely the brain's biochemistry, or do they hint at something more? The containment principle suggests only their physical roots belong to the universe, reducing joy to neural signals, love to chemical cascades. Picture a symphony played on a violin. The notes are vibrations of strings, yet the music feels beyond the wood and bow. Is consciousness just the brain's music, or does it echo a reality the universe can't contain? This raises existential questions. If the universe holds only the physical, what of the self that questions its own existence? In the 18th century, Bishop Berkeley proposed that reality depends on perception, that objects exist because they're observed. Extend this to the cosmos. Does the universe require a mind to be real, or does it persist independently? As realism asserts, the containment principle leans toward realism, claiming galaxies beyond our horizon, 46 billion light-years away, exist, though their light will never reach us. Yet, Kant's distinction between phenomena, what we perceive, and noumena, things as they are, suggests we may never grasp the universe's true nature, only its appearance through our senses and tools. Consider a photon crossing a galaxy, unaware of the minds pondering its path. That photon's reality doesn't depend on observation, yet our knowledge of it does. The universe's physicality, from quarks to galaxy clusters, exists objectively, but our understanding is bound by perception. This boundary isn't spatial, but epistemological. What can we know the multiverse, explored earlier, pushes this further. If other universes exist with different constants, their realities are forever beyond our grasp, like stories written in a language we can't read. The anthropic principle, noting our universe's life-friendly constants, suggests we're here because this reality allows it, but doesn't explain why such a reality exists. What if consciousness itself shapes cosmic boundaries? Imagine a universe where every sentient being's observations collapse quantum possibilities, as in quantum mechanics, where measuring a particle's state fixes its reality. In our universe, an electron's spin is uncertain until observed, collapsing a wave of probabilities into a definite state. Across billions of light-years, an alien mind might collapse a photon's state, subtly weaving the cosmos's fabric. This speculative idea, inspired by the bootstrap principle, suggests the microcosm of minds reflects the macrocosm of the universe. Anaxagoras, in ancient Greece, claimed everything contains a portion of everything else. Could consciousness be a cosmic thread, linking observers to the reality they perceive? This echoes Mach's principle, which posits a body's inertia depends on all other masses in the universe. Picture a lone asteroid spinning in space, its motion defined not just by local forces, but by the distant tug of every star. Similarly, consciousness might emerge not from isolated brains, but from the universe's interconnected web. a network of physical interactions spanning galaxies? If so, the boundary between observer and observed blurs, suggesting our questions about the cosmos are part of its fabric. The containment principle, though, insists this interplay remains physical, rooted in space-time, not some ethereal realm. Yet, the universe's vastness humbles such speculation. Beyond our horizon, galaxies drift, their stars igniting and fading, perhaps hosting minds asking the same questions. The cosmic microwave background, uniform across the sky, hints at a shared history, but its faint variations seeded galaxies will never see. These unobservable realms challenge our sense of centrality. The location principle denies Earth a special place, yet our consciousness feels unique, a solitary lens on a cosmos too vast to comprehend. Picture a single wave on an ocean, aware only of its own crest, yet part of a boundless sea. Are we such waves, or does our awareness hint at a deeper role? These questions probe the universe's purpose, if any. Deists, like William Paley in 1802, saw design in nature's complexity, likening the cosmos to a watch implying a watchmaker. Modern science, through natural selection and physics, explains complexity without intent. Yet the fine-tuning of constants like gravity's precise strength revives the debate. Is the universe a cosmic accident, one of many, or a singular reality crafted for life? The containment principle sidesteps purpose, focusing on what is physical, measurable, and real. Still, the human mind, bound by this principle, reaches beyond, asking why atoms exist, why time flows, why we ponder at all. This boundary of knowledge, like the cosmic horizon, isn't a barrier but a frontier. Each question, like a photon's journey, carries us closer to understanding. Even if the ultimate reality remains elusive, the universe, with its 100 billion galaxies, holds answers in its stars, its voids, and perhaps in the minds that contemplate them. Each a spark in the cosmic dark, seeking to illuminate what lies within and beyond. A neuron fires in your brain, sparking a thought about the stars overhead, each a distant furnace burning for billions of years. That thought, fleeting and intangible, arises from physical processes, atoms, electrons, and chemical bonds, yet feels distinct, as if it transcends the matter that birthed it. This tension between mind and matter mirrors a deeper question: what defines the universe's reality? The containment principle asserts that everything physical, stars, galaxies, even the space between them, exists within the universe, and nothing physical lies beyond. Space and time, not mere voids, are active players, bending under gravity's pull, stretching with cosmic expansion, as real as the ground beneath your feet. Picture a tapestry woven from space-time. Its threads the orbits of planets, the arcs of light from distant quasars. This tapestry holds all that is physical, from the plasma in a star's core to the faint cosmic microwave background, glowing since the universe was 380,000 years old. Archytas, in the 5th century BC, challenged the idea of a cosmic edge, asking what happens to a spear hurled beyond the universe's limit. Lucretius, centuries later, argued no such limit exists, as any boundary implies something beyond. Modern cosmology agrees the universe, whether infinite or finite, has no edge. A finite cosmos might curve back on itself, like a globe where every path returns home, but no wall marks its end. This principle excludes the non-physical. Imagine a realm of pure thought, untouched by matter or time. Such a place, if it exists, lies outside the universe's physical bounds, inaccessible to telescopes or equations. Yet, your thoughts, emotions, and consciousness emerge from physical processes: neurons firing, synapses crackling. Are they merely the brain's biochemistry, or do they hint at something more? The containment principle suggests only their physical roots belong to the universe, reducing joy to neural signals, love to chemical cascades. Picture a symphony played on a violin. The notes are vibrations of strings, yet the music feels beyond the wood and bow. Is consciousness just the brain's music, or does it echo a reality the universe can't contain? This raises existential questions. If the universe holds only the physical, what of the self that questions its own existence? In the 18th century, Bishop Berkeley proposed that reality depends on perception, that objects exist because they're observed. Extend this to the cosmos. Does the universe require a mind to be real? Or does it persist independently? As realism asserts, the containment principle leans toward realism, claiming galaxies beyond our horizon 46 billion light-years away exist, though their light will never reach us. Yet, Kant's distinction between phenomena, what we perceive, and noumena, things as they are, suggests we may never grasp the universe's true nature, only its appearance through our senses and tools. Consider a photon crossing a galaxy, unaware of the minds pondering its path. That photon's reality doesn't depend on observation, yet our knowledge of it does. The universe's physicality, from quarks to galaxy clusters, exists objectively, but our understanding is bound by perception. This boundary isn't spatial but epistemological. What can we know the multiverse, explored earlier, pushes this further. If other universes exist with different constants, their realities are forever beyond our grasp. Like stories written in a language we can't read, the anthropic principle, noting our universe's life-friendly constants, suggests we're here because this reality allows it, but doesn't explain why such a reality exists. What if consciousness itself shapes cosmic boundaries? Imagine a universe where every sentient being's observations collapse quantum possibilities, as in quantum mechanics, where measuring a particle's state fixes its reality. In our universe, an electron's spin is uncertain until observed, collapsing a wave of probabilities into a definite state. Across billions of light-years, an alien mind might collapse a photon's state, subtly weaving the cosmos's fabric. This speculative idea, inspired by the bootstrap principle, suggests the microcosm of minds reflects the macrocosm of the universe. Anaxagoras, in ancient Greece, claimed everything contains a portion of everything else. Could consciousness be a cosmic thread, linking observers to the reality they perceive? This echoes Mach's principle, which posits a body's inertia depends on all other masses in the universe. Picture a lone asteroid spinning in space, its motion defined not just by local forces, but by the distant tug of every star. Similarly, consciousness might emerge not from isolated brains, but from the universe's interconnected web, a network of physical interactions spanning galaxies. If so, the boundary between observer and observed blurs, suggesting our questions about the cosmos are part of its fabric. The containment principle, though, insists this interplay remains physical, rooted in space-time, not some ethereal realm. Yet, the universe's vastness humbles such speculation. Beyond our horizon, galaxies drift, their stars igniting and fading, perhaps hosting minds asking the same questions. The cosmic microwave background, uniform across the sky, hints at a shared history, but its faint variations seeded galaxies will never see. These unobservable realms challenge our sense of centrality. The location principle denies Earth a special place, yet our consciousness feels unique, a solitary lens on a cosmos too vast to comprehend. Picture a single wave on an ocean, aware only of its own crest, yet part of a boundless sea. Are we such waves? Or does our awareness hint at a deeper role? These questions probe the universe's purpose. If any, deists, like William Paley in 1802, saw design in nature's complexity, likening the cosmos to a watch implying a watchmaker. Modern science, through natural selection and physics, explains complexity without intent. Yet the fine-tuning of constants like gravity's precise strength revives the debate. Is the universe a cosmic accident, one of many, or a singular reality crafted for life? The containment principle sidesteps purpose, focusing on what is physical, measurable, and real. Still, the human mind, bound by this principle, reaches beyond, asking why atoms exist and exist, why time flows, why we ponder it all. This boundary of knowledge, like the cosmic horizon, isn't a barrier, but a frontier. Each question, like a photon's journey, carries us closer to understanding. Even if the ultimate reality remains elusive, the universe, with its 100 billion galaxies, holds answers in its stars, its voids, and perhaps in the minds that contemplate them, each a spark in the cosmic dark, seeking to illuminate what lies within and beyond.
A faint streak crosses the night sky, unnoticed at first by human eyes. In mid-October 2017, a telescope perched on a Hawaiian volcano captures it, a dim speck racing through the void. Unlike the asteroids or comets that drift in orderly paths around the sun, this object moves with reckless speed, unbound by the star's gravity. It slices through the solar system, a traveler from beyond, caught only in its fleeting exit. Astronomers, alerted by the Pan-STARRS telescope, turn their instruments toward it, but time is short. Within weeks, it fades into darkness, leaving a trail of questions. Named Oumuamua, a Hawaiian term for a messenger arriving first from afar, this object defies the familiar. Most celestial bodies in our system orbit the sun, tethered by its pull. Planets, asteroids, comets all follow predictable arcs, but Oumuamua, hurtling at 26 kilometers per second, traces a hyperbolic path, a one-way journey through our cosmic neighborhood. Its trajectory, tilted against the plane of the planets, suggests it came from deep space, perhaps another star system 30 to 80 light-years away. The light we see from it began its journey centuries ago, a snapshot of a distant past. At first, scientists assume it's a comet, an icy wanderer warmed by the sun, shedding gas and dust in a glowing tail, but no tail appears. Telescopes, including the Hubble, scan for the telltale coma, a fuzzy halo of vaporized ice, but find only silence. Perhaps an asteroid. Then, a rocky fragment cast adrift, yet its surface gleams, more reflective than the dull stones orbiting nearby. The Spitzer Space Telescope, sensitive to infrared, stares for 30 hours, seeking heat from sublimating ice. It detects nothing. Oumuamua, a few hundred meters long, slips through categories, neither comet nor asteroid. Its shape deepens the enigma. As it tumbles, its brightness surges and dips every 8 hours. A lighthouse beam in the void. This pattern, captured by ground-based observatories, reveals an object elongated, perhaps 10 times longer than wide a cosmic needle, or a flattened disk spinning chaotically. Asteroids in our system, battered into potato-like clumps, rarely stretch so far. Comets, spherical when dormant, sprout tails near the sun. Oumuamua's form, unlike anything local, hints at an origin where different forces sculpted its frame. The object's speed, faster than any natural body we've tracked, suggests a long exile. Ejected from its home system perhaps by a stellar collision or planetary tug, it drifted for millions of years, battered by cosmic rays. Its surface, shiny yet scarred, bears the marks of this journey. Astronomers, racing to analyze data before it vanished, calculate its path. Entering from the direction of Lyra, near the star Vega, it swings past the sun, then exits toward Pegasus. But Vega, 25 light-years away, moved long ago. Oumuamua's origin blurs, a trail lost in the galaxy's churn. As it recedes, a stranger anomaly emerges. After rounding the sun, Oumuamua should slow, its energy sapped by gravity. Instead, it accelerates, a faint but measurable push defying Newton's laws. This non-gravitational force, detected in precise orbital tracks, baffles researchers. No visible gas jets, no dust trails explain it. The object, silent and sleek, moves as if propelled by an unseen hand. Scientists scramble, checking calculations, ruling out errors. The acceleration, though small, is real, a whisper of something new. Initial theories point to solar radiation pressure, the gentle nudge of sunlight photons. Solar sails, human-designed craft, use this force to glide through space. If Oumuamua were a thin, lightweight sheet, sunlight might push it, but its tumbling motion and lack of heat emission clash with this idea. A comet-like outgassing, where ice vaporizes into jets, seems plausible, yet the absence of a coma undermines it. The object's behavior reflective, elongated, accelerating resists every model, a puzzle carved from the stars. Astronomers, limited to weeks of observation, gather scraps of light. The Canada-France-Hawaii telescope maps its spectrum, seeking chemical clues, but finds little beyond a reddish hue, typical of irradiated surfaces. The Very Large Telescope in Chile tracks its motion, confirming its interstellar roots, By December 2017, Oumuamua is too faint, slipping beyond reach. Its brief visit, a mere glimpse, leaves humanity with data too sparse to decode its nature. Yet the questions it raises ripple outward, challenging the boundaries of what we believe possible. Oumuamua's fading light lingers in the data, a cipher from the cosmos. Its acceleration, defying gravity's pull, sparks fierce debate. Solar radiation pressure, the force of sunlight on a thin surface, seems a logical culprit. Engineers at NASA have long studied solar sails' gossamer sheets propelled by photons. If Oumuamua were such a structure, perhaps a natural flake of exotic material, sunlight could nudge it faster. But its chaotic spin, like a bottle tossed forward, suggests a denser body, not a fragile sail. Its reflectivity, brighter than local rocks, lacks the uniformity of a crafted surface. Another theory posits outgassing, like a comet's jets. When comets near the sun, their ices water, carbon dioxide sublimate, thrusting them off course. Oumuamua, passing within 1/4 the Earth-Sun distance, should have warmed enough to vent gas, yet no trace appears. The Spitzer Space Telescope, designed to catch faint emissions, sees no dust or gas. Ground-based scopes, like the Gemini Observatory, find no coma. If outgassing drives its speed, it's invisible, a ghost comet unlike any known. This absence forces scientists to rethink what materials could act so subtly. Daryl Seligman, a researcher at Cornell, proposes a radical idea: Oumuamua as a hydrogen iceberg. In the frigid depths of molecular clouds, where stars are born, hydrogen can freeze solid. Such a body, heated by the sun, might release pure hydrogen gas, undetectable by our instruments. This could explain the acceleration without a visible tail. But critics, including Harvard's Avi Loeb, counter that hydrogen ice is fragile, evaporating under starlight long before reaching us. Oumuamua, intact after eons, seems too robust for such a delicate form. Jennifer Bergner, at UC Berkeley, offers a simpler twist. Oumuamua could be water ice, bombarded by cosmic rays over millions of years. In lab experiments, such irradiation traps hydrogen gas in ice's lattice. Near a star, this ice restructures, releasing hydrogen in tiny bursts enough to push a small object without spraying dust. This dark comet, as Bergner calls it, mimics a rock but acts like a comet, its activity hidden. The theory fits known physics, using common materials, yet Oumuamua's shape and shine stretch its plausibility. Avi Loeb, a Harvard astrophysicist, challenges these natural models. Oumuamua's anomalies, its elongation, reflectivity, acceleration, don't align neatly with comets or asteroids. He suggests a bolder possibility: alien technology. A light sail, a millimeter-thick craft designed to ride starlight, could match Oumuamua's behavior. Its acceleration, driven by solar photons, needs no gas. Its shape, flat or needle-like, fits a constructed object. Loeb's calculations show a thin, reflective surface could survive interstellar travel, tumbling from a long-ago collision. The idea, published in peer-reviewed papers, ignites controversy. The scientific community splits. Some dismiss Loeb's hypothesis, citing Occam's razor-simpler explanations, like exotic ices, should come first. Others, intrigued, argue the universe's vastness makes alien artifacts plausible. Loeb, undeterred, launches the Galileo project, seeking physical evidence of extraterrestrial technology probes, satellites, relics. He critiques science's caution, urging openness to ideas that challenge dogma. Oumuamua, he argues, exposes our bias toward the familiar, a failure to imagine beyond Earth's templates. The object's shape, inferred from brightness swings, fuels this debate. If a disk, it might resemble a sail, its spin a relic of ancient forces. If a cigar-like rod, it could be a fragment of a larger structure. No telescope resolved its form, leaving room for speculation. Simulations at institutions like Caltech model its tumble, suggesting a violent ejection from its home system. A planetary disruption, where a star's gravity tears worlds apart, could launch such shards, their shapes forged in chaos. Oumuamua's surface, reddish from cosmic ray bombardment, offers few clues. Spectra from the Keck Observatory show a hue like Kuiper Belt objects, irradiated over eons, yet its reflectivity, 10 times brighter than typical asteroids, hints at a smoother or icier composition. The lack of infrared glow puzzles researchers. Comets, warming near the sun, emit heat. Oumuamua's silence suggests a cold, inert body or something engineered to absorb little energy. Each datum, meticulously gathered, deepens the riddle. The acceleration, tracked by the European Southern Observatory, remains the crux. Its push, equivalent to a feather's nudge, grows stronger as Oumuamua recedes. This pattern matches solar radiation pressure, which weakens with distance, but not outgassing, which spikes near the sun. Loeb's sail fits this curve, yet natural theories persist. Nitrogen ice, like Pluto's surface, could sublimate invisibly, but its rarity in interstellar space strains credulity. Each hypothesis, tested against sparse data, falters under scrutiny. Astronomers turn inward, seeking analogs in our system. Seligman's team scans near-Earth asteroids, finding 6 with subtle non-gravitational shifts. These objects, small and rocky, lack cometary tails but move as if pushed. 1998, KY26, a 30-meter speck, spins every 10 minutes. JAXA's Hayabusa 2, fresh from Ryugu, targets it for a 2030 flyby. If it vents hidden gas, it could confirm the dark comet theory, linking Oumuamua to local cousins. The mission, a chance to touch the puzzle, carries humanity's hope for answers. These dark comets, if real, suggest Oumuamua wasn't unique. The solar system, once a closed bubble, emerges as a crossroads. Jupiter's gravity snares passing objects, some lingering in odd orbits. Asteroid 514107, Kaipioa-Wila, locked in resonance with Jupiter, may be interstellar, its chemistry alien. Comets like Hale-Bopp, rich in carbon monoxide, hint at distant origins. Each discovery, catalogued by observatories like Arecibo, reveals a galaxy where wanderers are common. The galaxy's highways hum with travelers, and Oumuamua was not alone. In August 2019, Gennady Borisov, an amateur astronomer in Crimea, spots another intruder named 2I Borisov. It blazes through the solar system, a comet with a glowing coma and a tail stretching tens of thousands of kilometers. Unlike Oumuamua's silence, Borisov announces itself, venting gas and dust as it nears the sun. Its carbon monoxide, abundant beyond local comets, points to a birthplace in a colder stellar nursery, perhaps 100 light-years away. Its hyperbolic path, like Oumuamua's, confirms an interstellar origin, entering from Hercules and exiting toward Telescopium. Telescopes, including the Swift Observatory, track its outgassing, a textbook comet born under another star. Yet its contrast with Oumuamua sharpens the mystery. One visitor, loud and bright, fits known physics. The other, sleek and silent, defies it. Together, they suggest a galaxy teeming with diverse wanderers, some visible, others elusive. Estimates from the University of Hawaii suggest thousands of interstellar objects cross Neptune's orbit daily, most too small or faint to see. The solar system, a speck in the Milky Way's spiral, lies on a busy route. Massive planets like Jupiter act as nets, temporarily capturing passers-by. Objects like Comet Makemake, with alien chemistries, may be relics of such encounters. These findings, published in Nature, reshape our view, casting the sun's domain as a galactic interchange. Oumuamua's acceleration, still unexplained, drives the search for answers. Bergner's dark comet theory gains traction, as lab experiments mimic its behavior. Water ice, irradiated for eons, releases hydrogen in controlled bursts, matching Oumuamua's push, but its shape 10-to-1 elongation challenges this model. Simulations at MIT suggest a natural body stretched by tidal forces near a star, yet no known process yields such extremes. Loeb's sail, a constructed artifact, remains a shadow hypothesis, unprovable without more data. The object's origin, traced by supercomputers at Oxford, remains elusive. Its path, rewound through the galaxy's gravitational maze, points nowhere precise. Stars in Lyra, like Vega, drift too fast to align with Oumuamua's past. Clusters like the Pleiades, 50 light-years distant, offer possible birthplaces, but simulations yield no matches. The object, drifting for hundreds of millions of years, erases its tracks, its surface a palimpsest of cosmic weathering. Its journey, solitary and vast, began before humanity's first fires. Project Lyra, launched by researchers in London, dreams of pursuit, a spacecraft, using Jupiter's gravity and a solar slingshot, could reach 70 kilometers per second, catching Oumuamua by 2048, launching between 2030 and 2033. It would brave the sun's heat, navigating a needle's eye in deep space. Yet the object, now a faint speck, poses a challenge. Its tumble, unpredictable after decades, complicates targeting. The mission, costing billions, bets on a single chance to touch the unknown. Closer to home, the Vera Rubin Observatory in Chile prepares for the next visitor, set to scan the sky in 2025. Its legacy, survey of space and time, will map every flicker, catching dozens of interstellar objects yearly. Unlike Oumuamua, spotted weeks after its closest approach, future travelers may be seen months ahead, allowing probes to intercept them. The European Space Agency's Comet Interceptor, launching in 2029, waits in space, ready to chase an incoming comet or alien object, its instruments primed for close study. These missions, born from Oumuamua's wake, mark a shift. Humanity, once reactive, builds tools to anticipate. The Rubin's 10-year survey, imaging the sky every 3 nights, will catalog larger, slower visitors, their paths traceable. Interceptor's flexibility, orbiting a stable point, lets it pivot to new targets. Together, they promise a harvest of data, revealing how often the galaxy sends messengers and what they carry: ice, rock, or something stranger. Its acceleration, if driven by radiation pressure, inspires new sail designs at institutes like Caltech. If a dark comet, it redefines cometary physics, prompting studies of local asteroids. The 1998 KY-26 flyby, planned by JAXA, tests this theory. Its data a bridge to Oumuamua's nature. If alien, it challenges our search for life, pushing projects like SETI to scan for physical artifacts, not just signals. The galaxy, a spiral of 200 billion stars, hides countless such objects. Oumuamua's path, crossing ours by chance, suggests others wait unseen. The local bubble, a 1,000 light-year cavity around the sun, formed by ancient supernovae, may channel these travelers. Its hot gas a highway for debris. Ambrosita's X-ray maps, from orbits beyond Earth's atmosphere, hint at tunnels linking such bubbles. A galactic network where Oumuamua once roamed. Oumuamua's trail, now cold, stretches toward Pegasus, a speck lost in the void. Its brief passage, a mere month in our skies, rewrites our cosmic map. Borisov's arrival, 2 years later, confirms the galaxy's restlessness. Its coma, glowing with carbon monoxide, spans 50,000 kilometers. A beacon from a star system colder than ours, tracked by the Chandra X-ray Observatory. Its outgassing mirrors local comets, yet its chemistry rich in alien ices sets it apart. These 2 visitors, one cryptic, one open, hint at a spectrum of interstellar wanderers. The dark comet theory, tested by local asteroids, gains ground. 1998 KY-26, a 30-meter rock, spins furiously, its orbit nudged by unseen forces. Hayabusa 2's flyby, planned for 2030, will probe its surface, seeking hydrogen trapped in irradiated ice. If confirmed, dark comets could number thousands in our system, their subtle pushes reshaping orbital models. The Pan-STARRS survey, which found Oumuamua, now hunts these ghosts. Its data-feeding algorithms at the University of Arizona. Loeb's alien hypothesis, though divisive, spurs innovation. The Galileo project, funded privately, deploys telescopes to scan for artificial objects, probes, sails, or debris. Its arrays, dotting observatories in New Mexico, seek infrared signatures of technology, a shift from SETI's radio focus. Loeb's book, Extraterrestrial, argues Oumuamua's anomalies shape, shine, acceleration fit a crafted relic, perhaps a derelict probe from a civilization long gone. Critics, citing natural ices, demand proof, but the debate fuels curiosity. Oumuamua's acceleration, a tenth of a millimeter per second squared, remains the pivot. Models at the Max Planck Institute test exotic ice's methane, carbon monoxide sublimating, invisibly. None fully match the data. Solar radiation pressure, requiring a thin, reflective body, aligns better, yet Oumuamua's density, inferred from its tumble, suggests a solid core. The tension between theories drives experiments, from ice irradiation at CERN to sail prototypes at JPL. Each test, grounded in Oumuamua's clues, pushes science forward. The object's shape, a 10-to-1 ratio, haunts researchers. Tidal forces, stretching a body near a star, could form such needles, but require extreme conditions. Simulations at Stanford model a planet shredded by a white dwarf, launching elongated shards. Oumuamua, if such a fragment, carries a story of stellar violence. Alternatively, a flat disk, spinning like a coin, fits a sail's profile, its tumble a scar of ancient impacts. Without images, both shapes live in equations, a duality unresolved. The Rubin Observatory, its 8-meter mirror scanning Chile's skies, will spot them monthly, its deep exposures catching faint glints. Comet Interceptor, parked at a Lagrange point, awaits a slow-moving target, its spectrometers ready to parse alien ices. These tools, inspired by Oumuamua's escape, aim to catch travelers early, orbiting them for months. Such missions, planned by ESA and NASA, could sample surfaces, revealing compositions forged under distant suns. Its solar Obearth maneuver, firing engines near the sun, demands precision. A probe, shielded against solar heat, would race past Oumuamua, imaging its surface at 20 kilometers per second. The data, beamed back by 2050, could show craters, fractures, or artificial seams. The mission's risk, a decades-long gamble, reflects humanity's drive to grasp the fleeting, a quest born in Oumuamua's wake. Formed 10 million years ago by supernovae, it spans 1,000 light years, its edges birthing stars. Oumuamua, passing through, may have ridden its currents, guided by plasma tunnels mapped by Erosita. These channels, linking bubbles across the galaxy, suggest a cosmic web where objects drift. Borisov, too, navigated this network, its path a thread in the Milky Way's tapestry. Humanity's watch extends beyond Oumuamua. Ancient Polynesians, navigating by stars, saw the same sky, unaware of its travelers. Today, amateurs with 10-inch scopes contribute to surveys, their data vital. The American Association of Variable Star Observers, logging Oumuamua's brightness, feeds global models. This blend of citizen and professional science, amplified by AI, scans for the next visitor, a collective effort to meet the galaxy's messengers. The galaxy itself, 200 billion stars strong, pulses with motion. Oumuamua's path, a chance crossing, mirrors countless others. Kaiapawawela, orbiting backward with Jupiter, may be a captured wanderer, its orbit a fossil of interstellar exchange. Comets like Hyakutake, their ice is alien, reinforce this flow. Each object, studied by telescopes like ALMA, reveals a solar system porous to the stars, a stage for cosmic encounters. Oumuamua drifts toward Pegasus, a silent speck in the galaxy's depths. Its passage, brief and baffling, leaves a trail of light and questions. Borisov, its cometary cousin, blazed through 2 years later, a reminder of the galaxy's restless traffic. Together, they reveal a solar system not isolated, but woven into the Milky Way's fabric, a crossroads where alien objects pass daily. The Rubin Observatory and Comet Interceptor, poised for action, stand ready to greet the next, their lenses and probes a bridge to the unknown. The object's acceleration, a faint push against the sun's pull, anchors the mystery. Bergner's dark comet, water ice venting invisible hydrogen, offers a natural path, grounded in lab tests. Loeb's light sail, a whisper of alien craft, challenges orthodoxy, urging science to stretch. Between them lie theories of exotic ice's nitrogen, Methane each tested, each flawed. Oumuamua's shape, elongated or flat, and its reflective surface defy easy answers. A riddle etched in starlight. The 1998 KY-26 flyby, probing local dark comets, may clarify its nature, linking the alien to the familiar. Project Lyra's dream, chasing Oumuamua to 2048, embodies humanity's resolve. Its solar slingshot, a fiery gamble, aims to capture images of a tumbling relic, be it rock or relic. The mission, though distant, echoes the Vera Rubin's vigilance, scanning for new travelers. These efforts, born from a single visitor, reshape astronomy, turning our gaze from static stars to dynamic intruders. The local bubble, its tunnels guiding such objects, frames this quest, a galactic stage where Oumuamua played its part. The galaxy's scale, 200 billion stars across 100,000 light-years, dwarfs our system. Oumuamua, ejected from an unknown star, drifted for eons, its origin lost in stellar orbits. Vega, once a candidate, drifts too far. Clusters like the Hyades offer no firm link. Yet its journey, scarred by cosmic rays, speaks of a universe in motion, where planets shatter and stars collide. Borisov, Kayapawawela, and others trace similar paths. Their chemistry's a record of distant worlds. Humanity's response, from Hawaiian telescopes to global observatories, shows a species awake to the cosmos. Ancient Sumerians, charting stars 5,000 years ago, saw the same sky, their clay tablets marking time. Today, we parse light with silicon, our data a modern epic. Amateurs, logging Oumuamua's flickers, join professionals at Keck and Hubble, a shared pursuit. This unity, sparked by a fleeting visitor, drives missions like Interceptor, ready to touch the next messenger. Its anomalies' speed, shape, acceleration force science to question assumptions. Dark comets, if real, redefine our system's boundaries. A sail, if true, redefines life's reach. Each theory, from Seligman's ice to Loeb's craft, pushes boundaries, sparking experiments and debates. The Galileo Project, scanning for artifacts, and Rubin's Sky Survey, hunting wanderers, carry this forward, a search for truths beyond our templates. The solar system, once a closed orbit, emerges as a galactic hub. Comets from the Oort cloud, nudged by passing stars, link us to the Milky Way's churn. The local bubble, carved by ancient explosions, channels these flows, its plasma tunnels a cosmic road. Oumuamua, Borisov, and future visitors ride these currents, their paths a story of creation and chaos. Humanity, watching from a blue speck, meets them with wonder, our tools and dreams aimed at the stars.